Hello everyone, welcome to the first lesson of IGCSE Physics ATP paper crash course. Students, before we jump into the lesson, let me first quickly tell you two very important things about the ATP paper. The grade threshold for an A grade in this paper and the structure of the paper. Students, ATP paper is a 40 marks paper and you'll be surprised to know that the average grade threshold for an A grade in this paper is only about 26, which means that if you are given an ATP paper of every difficulty level, then you can lose about 14 marks out of 40 and still expect to get an A in it. But students, you must also note that you cannot always get an A grade in this paper by scoring about 26 marks in it, because the grade threshold for any grade actually depends on the difficulty level of the paper. So 26 is actually the grade threshold for an A grade in an ATP paper of every difficulty level. However, for a relatively easy paper, the grade threshold for an A grade is usually higher than 26, and similarly, for a relatively difficult paper, the grade threshold for an A grade is usually lower than 26. Students, you might also find it surprising that the lowest grade threshold for an A grade in the ATP paper in the past 10 years has been as low as 19, which is even less than 50% of the total marks. And on the other hand, the highest grade threshold for an A grade in the ATP paper in the past 10 years has been as high as 31, which is close to 80% of the total marks. Okay, students, let's look at the structure of the ATP paper now. Students, in the past, the IGCSE Physics ATP paper consisted of 5 questions, but it now consists of 4 questions. The first 3 questions are usually for 11 marks each. These questions are relatively easy, but the last question, question 4, which is referred to as the planning question, is considered to be the most difficult question in the paper by most of the students. But the good thing about the planning question is that it's only for 7 marks. So even if you mess up the planning question, you can still secure an A grade in your paper. Students, it's also important to know that the ATP paper questions are usually on these 6 topics only: oscillations, equilibrium and general physics, spring extension and Hooke's law, cooling rate and thermal insulators, light and electricity. Now students, note that not all of these topics are equally important. For example, these 3 topics are more important than these 3 topics. I'm saying this because if you go through several ATP past papers randomly, you will almost always find in every ATP paper one question on cooling rate and thermal insulators, one question on light, and one question on electricity. And this is not the case with these 3 topics. So students, this was a quick overview of the structure of the ATP paper. Let me tell you the plan of work now. Students, this crash course consists of 7 lessons. In lesson 1, we will first learn 6 general rules that are used in all ATP papers. These rules include rules for stating values of calculated or measured quantities with the appropriate units and to appropriate number of significant figures or decimal places. They also include rules for writing column headings, labeling graph axis, and determining percentage difference between two values of a quantity to see if the quantity may be regarded as constant or not. Students, after learning these 6 general rules, we will do 2 questions on oscillations in our ATP paper workbook and see how these rules are used in different parts of the ATP paper questions. Students, you can download the printable PDF file of the ATP paper workbook by clicking the link given in the description down below. Let me show you what the workbook looks like. See students, this is the front title of the workbook. This is the content list. You can see that the workbook contains questions on all 6 topics the ATP paper questions are usually on. Students, I have handpicked these questions from different past papers, and I'm quite positive that if you do all the questions in this 104 pages workbook, then you can easily secure an A grade in your actual ATP paper exam. And students, to assist you guys further, I've also written the solution to the whole workbook. Let me show you the solved workbook now. See students, This is the solve workbook. It contains solutions to all workbook questions along with explanation. So students, if you get stuck on any question or on any part of a question, you can get help from this solution file. I'm leaving the link for the solution file in the description too, so you can download it from there. Okay, students, let's go back to the plan of work now. So in lesson 1, we will learn 6 general rules used in all ATP papers first and then do questions on oscillations in the workbook. In lesson 2, students, we will do questions on equilibrium and general physics. In lesson 3, we will do questions on spring extension and Hooke's law and also learn rules for plotting a graph when doing the question. Students, there are 4 rules or steps involved in plotting a graph, by the way. Then in lesson 4, students, we will do questions on cooling rate and thermal insulators. And in lesson 5, we will do questions on light and also learn rules for determining the gradient of the line of best fit when doing the questions. Students, there are only 2 rules needed to be learned here. Then in lesson 6, students, we will do questions on electricity. And in the last lesson, lesson 7, we will do some planning questions. So this is the whole plan of work. Let's jump into today's lesson, lesson 1 now. Students, the first thing you should all learn when preparing for the ATP paper is the set of these 6 general rules because these rules are used in all ATP papers. So students, it's very important that you learn and remember all of them. Let's learn the first rule first. The first rule says, always state the value of a quantity along with the appropriate unit. For example, students, the distance between 2 points should be stated as 5.6 centimeters, not as just 5.6 with no unit. Students, of all the rules that you will learn in this crash course, this rule is perhaps the easiest and also the most important rule because you can lose about 2 or 3 marks in your ATP paper if you don't state unit after the value of a measured or calculated quantity. Let's learn the next rule with the help of an example this time. Students, we all know that the least count of a typical meter rule is 0.1 centimeter, right? So a length of 2 centimeter measured with a meter rule should be stated as 2.0 centimeter and not as just 2 centimeter. Let me explain why. Actually, students, the relevant rule here says that the measured quantity should be stated to the same number of decimal places as the least count of the measuring instrument. Now look, here the value of least count of meter rule has 1 decimal place. So the value of length measured with a meter rule should also be stated to 1 decimal place and not to any other number of decimal places, right? Let's move on to the next rule now. We will learn this rule with the help of an example too. If distance t of 0.050 meters is covered in time t equals 0.0581 seconds and speed is given by the expression d by t, then calculate and state the value of v to appropriate number of significant figures. Students, let's determine the value of v first. V is equal to d by t, where d is 0.050 meters and t is 0.0581 seconds. So the speed comes out to be 0.860585 meters per second. Now see students, the calculated value of v has too many significant figures and it needs to be rounded off. But the question is to how many significant figures? Let's see what the relevant rule says here. The rule says that the number of significant figures to be retained in the calculated quantity should be equal to the least number of significant figures in the raw data. Now in this example, students, d and t make the raw data because we use the values of d and t to calculate v, right? Now in our raw data, d has 2 significant figures, 5 and 0. As these zeros, the leftmost zeros in the decimal value are non-significant, and t has 3 significant figures, 5, 8 and 1. Here again, students, these zeros are non-significant. Now look students, in the raw data, d has the least number of significant figures, which is 2. So according to the rule, the calculated value of v should be rounded off to 2 significant figures, that is, to this digit. Now if we round off the value of v to this digit, we get 0.86 meters per second. So see students, this is how we round off the calculated value of a quantity to appropriate number of significant figures if the value is obtained by multiplication or division, right? Let's learn the next rule now. Students, we will learn this rule with the help of an example too. If x is equal to 2.3 centimeters and y is equal to 1.964 centimeters, then calculate and state the value of x plus y to appropriate number of decimal places. Okay, students, let's calculate the value of x plus y first. X is 2.3 centimeters and y is 1.946 centimeters. So x plus y is calculated as 4.246 centimeters. Now students, we have to round off this value to appropriate number of decimal places. Let's see what the relevant rule says here. The rule says that number of decimal places to be retained in the calculated quantity should be equal to the least number of decimal places in the raw data. Now in this example, students, x and y serve as the raw data. And you can see that the value of x has one decimal place and the value of y has three decimal places. Now as x has the least number of decimal places, which is 1, so according to the rule, the calculated value of x plus y should be rounded off to one decimal place, that is to this digit. Now rounding off the value of x plus y to this digit gives 4.2 centimeters. See students, this is how we round off the calculated value of a quantity to appropriate number of decimal places if the value is obtained by addition or subtraction, right? Students, before we move any further, I want you to understand and remember the difference between the last two rules that we have just learned. Students, I want you to remember that we round off the calculated value of a quantity to appropriate number of significant figures if the value is obtained by multiplication or division, whereas we round off the calculated value of a quantity to appropriate number of decimal places if the value is obtained by addition or subtraction. Okay, let's learn the next rule now. The next rule says that each column heading and similarly the labels of graph axis should contain both the physical quantity and its unit with a distinguishing mark, for example, forward slash mark separating the quantity from its unit. For example, students, let's say we have to write a column heading for time intervals that are expressed in seconds. Now, according to the rule, the column heading should be T, which represents the physical quantity time, then forward slash mark, and then unit of time, second. So see students, the heading contains both the quantity and the unit. And we also have a distinguishing mark that separates the quantity from the unit, right? Let's run the last rule now. Students, this rule is used to determine whether a quantity, say k, may be regarded as constant or not. Now to determine this, we have to first find the percentage difference between two values of the quantity. So let's first learn how to find the percentage difference between two values of a quantity. Students, the percentage difference between two values k1 and k2 of a quantity k is given by the expression difference between the two values over average of the values times 100. Now the difference between two values of k is expressed as k2 minus k1 and the average of the two values is expressed as k1 plus k2 over 2. So the percentage difference between two values of k is given by this expression. Now students, whether the quantity k may be regarded as constant or not depends on the size of the percentage difference between its two values. The rule says if the percentage difference between the two values of a quantity is less than 10%, then the quantity may be regarded as constant within the limits of experimental accuracy. Let me repeat it. If the percentage difference between the two values of a quantity is less than 10%, then the quantity may be regarded as constant within the limits of experimental accuracy. Students, this last part that says within the limits of experimental accuracy is very important and you should memorize it because in the actual ATP paper, when answering a question, we don't state the rule as such. Rather, we state our answer like this. In front of statement, we write yes if the quantity is constant, and in front of justification, we write the percentage difference between its two values is within the limits of experimental accuracy. On the other hand, students, if the quantity is not constant, then we write no in front of statement, and in front of justification, we write the percentage difference between its two values is beyond the limits of experimental accuracy. Students, we have just learned all 6 general rules used in every ATP paper. So learning these rules will go a long way in performing well in the ATP paper exam. Now that we have learned the general rules, let's do some questions on oscillations in our ATP paper workbook. Look students, this is the first question on oscillations. The question says that the IGCSE class is investigating a pendulum. Okay, the apparatus is shown in figure 5.1. See students, this is the pendulum he is referring to. This is the pendulum bob. held above this bench. And look, students, the length of the pendulum has been denoted by small l. Part A says on figure 5.1, measure the length small l of the pendulum. Let's do that. Let's measure the length small l with a 30 centimeter plastic rule. Now students, we know that the least count of a typical plastic rule is 0.1 centimeter, and the value of 0.1 centimeter has one decimal place. So the measurement of small l made with a plastic rule should also be stated to one decimal place, like this, 10.5 centimeters. Actually, students, I've already measured the length and I know that it measures as 10.5 centimeter. Let's do the next part now. Students, part B says the diagram is drawn 1/5 actual size. What does this mean? This means that the actual size of the objects shown in the diagram is 5 times greater. Calculate the actual length capital L of the pendulum. Now look students, as the actual length of the pendulum is 5 times its length shown in the diagram, so the actual length capital L is calculated as 5 times 10.5, which is equal to 52.5. So students, the actual length capital L of the pendulum should be stated as 52.5 centimeters, right? Let's do the next part now. The next part, part C says, a student places a meter rule on the bench so that 50 centimeter mark is vertically below the center of the pendulum bob. So students, if this is the pendulum bob and this is the center of the bob and this is the meter rule placed on the bench, then the 50 centimeter mark is here, vertically below the center of the pendulum bob, right? Describe how you would judge that 50 centimeter mark is vertically below the center of the pendulum bob. You may draw a diagram. Look students, in this part, to check if the 50 centimeter mark is vertically below the center of the bob, the student can use a set square. Let me show you how. See students, he can place the set square on the meter rule like this, so that the vertical edge of the set square, this edge, is on the 50 centimeter mark and also right below the bottom of the bob, this point. Students, this diagram will earn you full marks in this part. You don't have to write anything here because the diagram is already self-explanatory. It clearly shows what's going on. Students, there is a very important point you should remember about drawing a diagram in the ATP paper, that when you draw a diagram, label each and everything in your diagram. Otherwise, you may lose a mark. Let's do the next part now. Part D says the student pulls the pendulum bob to one side until it is vertically above the 52.0 centimeter mark on the rule. Okay, he has moved the pendulum bob a horizontal distance d equal to 2.0 centimeters. This makes sense because previously the bob was right above the 50 centimeter mark. He releases the pendulum bob, then measures the time small t taken for 12 complete swings of the pendulum. So students, now he can divide the time taken for 12 swings by 12 and determine the period of the pendulum. He repeats the procedure using a range of d values. The values of d and small t are shown in table 5.1. See students, these are the values of t and these are the corresponding values of small t. The third column, which is supposed to have corresponding values of period, capital T, is blank. Now D part 1 says, calculate the period capital T of the pendulum for each value of d. Enter the values in the table. The period capital T is the time taken for one complete swing of the pendulum. Look students, for d equal to 2 centimeters, the time taken for 12 swings is 17.4 seconds. Students, I have just figured out that the unit of time must be second because obviously the time taken for 12 swings of the pendulum can't be 17.4 minutes. So students, if time taken for 12 swings is 17.4 seconds, the time taken for one swing, that is the period of the pendulum, can be easily determined by dividing 17.4 by 12. So students, for d equal to 2 centimeters, period comes out to be 1.45 seconds. Let's determine the period of pendulum for d equal to 3 centimeters now. See students, here the time taken for 12 swings is 17.6 seconds. So the period is calculated as 17.6 divided by 12, which is equal to 1.46666666 and the value continues. Now here students, we need to round off this value to appropriate number of significant figures. We know the rule that the number of significant figures to be retained in the calculated quantity should be equal to the least number of significant figures in the raw data. Now students, here small t serves as the raw data and it has three significant figures. So the value of period should be rounded off to three significant figures, that is to this digit. Now rounding off the value of period to this digit gives us 1.47. Students, note that here the last digit retained in the value is increased by 1. So it changes from 6 to 7 because the last digit drop is 6 and 6 is greater than 5. Students, this is a standard rounding off rule that I'm sure you all must already know. Now students, use the same method as shown here and determine the rest of the values of period by yourself later because I am going to move on to the next part. The next part, D2 says, complete the column headings in the table. Students, note that each column heading in the table contains a quantity and a forward slash mark, but it lacks unit. So let's complete the column headings by adding appropriate units to them. We know that the unit of distance t is centimeter, the unit of time small t taken for 12 swings is second, and the unit of period capital T is also second. So now the column headings in the table are complete and we get 1 mark for that. Let's do the next part now. Part E says, using the evidence in the table, describe the effect on the period capital T of increasing the distance t. Justify your answer by reference to your results. Students, first of all, note that the value of t continuously increases from the first row until the last row, but the value of period t, on the other hand, increases a little bit from the first row to the second row, then decreases a little bit from the second row to the third row, and then increases a little bit again from the first row until the last row. In short, there is no trend in the values of period t, neither increasing nor decreasing. Also note that the values of period t are very close to each other, and apparently the percentage difference between any two values of t is less than 10%. So we can say that period t remains constant or the same. In other words, increasing t has no effect on period. And the justification for this answer is that the values of t are pretty much the same. And that's it. Let's do the next part now. The next part, part F, which is also the last part of the question, says that suggest why the student measures the time taken for 12 swings of the pendulum rather than for one swing. Students, if you could recall, we learned this concept in the first chapter of IGCSE physics syllabus, length and time, that when we time several oscillations of a simple pendulum and then divide the total time taken by the number of oscillations, we get the average value of the period, which is more accurate because it reduces the effect of human reaction error on the time measurement. So the answer to this part is to get an average value of t, or to get a more accurate value of t, or we can also write to reduce the effect of human reaction error. To reduce the effect of human reaction error. Students, we have just finished the first question on oscillation. Let's do the next question now. See students, this is the second question on oscillations in our ATP paper workbook. As you can see that parts A and B of this question are similar to some of the parts of the first question on oscillation that we have just finished. So I have already done them to save time. Let's start this question from part C. Part C says that the student adjusts the length of the pendulum until its length L is 61.9 centimeters. He repeats the procedure in B and calculates T. The results are shown in table 1.1. Look students, this is table 1.1. The first column contains two values of length small l of the pendulum. The second column contains the corresponding values of time small t taken for 20 oscillations, and the third column contains the corresponding values of period capital T of the pendulum. Let's go back to the question. The student suggests that doubling the length L of the pendulum should double the period. That is, the student suggests that the new value of period T prime for the length of the pendulum equal to 2L is 2 times its initial value, which is 1.12 seconds. See? So students, the new value of period according to student's suggestion should be 2.24 seconds. State whether the results support this suggestion and justify your answer by reference to the results. Let's go back to the table one more time. Students, note that the results in the table show that when we double the length of the pendulum, the period of the pendulum also increases, but it does not double. Look students, the actual value of the period of the pendulum when its length is doubled is 1.58 seconds, whereas the value suggested by the student is 2.24 seconds. Now students, to determine whether or not the results support the suggestion made by the student, we need to calculate what? Percentage difference. Percentage difference between the two values of period, the actual value and the suggested value. The percentage difference between these values is calculated as 35%, which is greater than 10%, which means that the results do not support the suggestion of the student. So the answer to part C is no. And justification for the answer is the percentage difference between the suggested value and the actual value of period is beyond the limits of experimental accuracy. Right? Let's do the next part now. The student repeats the procedure in D for 4 times with different lengths of the pendulum. Okay. The student plots a graph of L against T squared. State 2 pieces of information from the graph that would indicate that L is directly proportional to T squared. Look students, we know that when two quantities, say L and T squared, are directly proportional to each other, their graph is straight line and passes through the origin. So what two pieces of information would indicate that L is directly proportional to T squared? The graph will be straight line and pass through the origin. Right? Students, the next part, part E, is similar to part E of question 1 that we have already done. So I'm leaving this part as homework for you. You can do it by yourself later. Students, this later homework marks the end of our first lesson. I'll see you soon in the next lesson. Take care and stay blessed.